So I will talk today about almost optimal testers for concise representations. Okay, so the model of testing, given a class C of Boolean functions, given a black box that contains any Boolean function f, the algorithm has an access to two oracles. The first returns the value of the function f in x, and the second oracle returns a random string u in 0, 1 to the n according to a distribution d that is unknown to the algorithm or to the tester. A distribution-free tester A for the class C is an algorithm that has access to those oracles and to a distance parameter epsilon, such that if f is in C, then with probability at least 2/3 the tester accepts. And if f is epsilon far from every function in C with respect to the distribution D that is unknown to the tester, then with probability at least 2/3 the tester reject. Here, epsilon far from every function in C means that for every h in C, the probability that f is not equal to h is at least epsilon with respect to the distribution D. So here is the class C. If f in C, then the tester accepts with probability at least 2/3. And if f is epsilon far from C with respect to distribution D, then the tester rejects with probability at least 2/3. One interesting class is the class of K junta. K junta is a Boolean function that depends on at most K coordinates. Here is an example of 3 junta. It depends on 3 coordinates or variables. It is also 4 junta because it depends on at most 4 coordinates. We call the coordinates that f depends on relevant coordinates or relevant variables. The class of K junta is the class of all such functions. We're interested in constructing tester for subclasses of K junta, subclasses that are symmetric. That is, if f is in C, then for any permutation phi of the indices of the variables, x phi 1 to x phi n is also in C. And C is closed under zero projection. That is, if f in C, then projecting any variable to 0 gives a function in C. Now all the interesting classes known from the literature satisfy those two properties. For such classes, we're interested in testers that run in polynomial time and ask minimum number of queries independent on n. For some classes, we will not be able to get polynomial time tester, but we do get a query complexity that is independent of n. Here is a paper that gave the first tester for such classes with query complexity independent of n, but under the uniform distribution. This paper gave a better query complexity, but again under the uniform distribution. Our result is the first that gives distribution-free tester with query complexity independent of n, and for some classes, testers under uniform distribution with optimal query complexity. We give some of our results. So for a monotone DNF with at most S terms, and each term is of size at most R, the best tester known was under the uniform distribution with this many queries. and exponential time. We gave a polynomial time tester under the uniform distribution with optimal query complexity and a distribution-free tester with query complexity independent of n. Here's another result for size S decision tree and size S branching program. We also here for uniform distribution, we have an optimal query complexity and a distribution-free tester with query complexity independent of n. Another result for the class of polynomial over F2, the field of F2 of degree D with at most S monomials. Again, those classes are subset of K junta. For example, this class, the number of variables in each such function is at most SD. So in this case, K equal SD, and this class is a subset of SD junta. Okay, so now I'll sketch the tester, and later I'll give more details. So given a subclass of K junta and epsilon, we may have two cases. The first case is when f is in the class C, and the second case is when f is epsilon far from every function in the class C with respect to some distribution D that is unknown to the tester. At the first stage, the tester uniformly at random chooses a partition of the coordinates into R equal to K squared pairwise disjoint sets x1 up to xr. Now, why 2K squared? Because if f is in C, then f has at most K relevant coordinates, and we want that with high probability every relevant coordinate of f falls into different xi. So from now on, we assume that if f in C, then every set xi contains at most one relevant variable. Now the tester searches for relevant sets xi. What is the relevant set? A set xi is relevant if it contains a relevant coordinate of f. Let xi1, xi2, xik be the relevant sets that the tester finds. Of course, if the number of relevant sets k prime is greater than k, then f is not K junta, and then it is not in C, and the tester rejects. So we can assume that k prime is less equal k. Let x be the union of the relevant sets that the tester finds. Now the tester may not be able to find all the relevant sets, so it finds enough relevant sets such that when we project the variable in x to the vector x and the other variables to 0, we get a function h that is epsilon over 3 close to f with respect to d. I'll explain later how to search for relevant sets and to ensure that h is close to f. Let us for now assume that the function h is epsilon over 3 close to f with respect to the distribution d. If f is in C, then since C is closed under 0 projection, h is also in C. If f is epsilon far from C, then since h is epsilon over 3 close to f, we have that h is 2 epsilon over 3 far from C. Now in the second stage, the tester substitutes in all the variables of each relevant set the variable that is relevant in this set. So, for example, if tau1 is the relevant coordinate in xi1, then the tester substitute the variable x tau1 in all the variables of xi1. Okay, now wait a minute. We do not know which variable is relevant in each set, and we cannot afford to find it, because finding it takes at least log n queries, and we want the number of queries to be independent of n. But let us for now assume that we can do this substitution. With this substitution, we get a function g. If h in C, we said that each set depends on one coordinate, and now we substitute the variables that correspond to this coordinate to all the variables in the set. So we get g equal to h. If h is 2 epsilon over 3 far from C, then either h is epsilon over 3 far from g with respect to d, or g is epsilon over 3 far from c with respect to d. So we can do two tests. The first test is testing if h is epsilon over 3 far from g with respect to d. Now assume we can query g. This need order of 1 over epsilon queries. The second test is testing if g is epsilon over 3 far from c with respect to d. But this time g depends on at most k variables, not n variables. So in this test, the number of queries is independent of n. The problem is, how do we query g? Well, to query g, we need h, and we need to know, given an assignment x, the value of the relevant variables in x. And we will show how to do that with self-corrector. Now, two missing details in this sketch. The first is how to find the relevant sets such that, enough relevant sets such that h is epsilon over 3 close to f. The second is how to query g without learning the relevant coordinates. Okay, so now how do we find the relevant sets? We said we take random partition. We want to find enough relevant sets such that projecting those sets to the vector x and the other sets to 0 gives a function that is close to f with respect to d. So now the algorithm. Suppose at some stage of the algorithm we found the relevant sets xi1, xi2, xij. Let those sets are the other sets. We define x to be the union of the relevant sets. We choose u according to distribution d and compare the current h with f. If they are equal for order 1 over epsilon strings u, then we know that the current h is epsilon over 3 close to f with respect to d, and we are done. If they are not equal for some u, then we do a binary search to find a new relevant set. Notice that those two vectors agree on x, which is the union of the relevant sets. So the binary search should give a new relevant set. How do we do the binary search? We take x complement, which is the union of all the sets x, s1, s2, up to sr minus j's that we do not know they are relevant, split them to two sets, y1 is the union of half the sets that, and y2 is the union of the other half. Then we compare those two with this. If those two are not equal, then we recursively do the search in the set in the sets in Y1. And if those two are not equal, then in Y2. This search ends up with a new relevant set. If we find more than k relevant sets, then we reject. Now, the query complexity is O tilde of k over epsilon. Why? Because we find up to k relevant sets. If we find more than k, then we reject. Each time we compare here, we have order of 1 over epsilon. Then it's k over epsilon, and the binary search is just log k, and this is why we have the tilde O. In addition to the relevant set that we find in the previous algorithm, we also find for the relevant set a witness. What is a witness? A witness is an assignment V such that changing the value of V in the set to 0 changes the value of the function. We call this a witness for the relevant set Z. We will use those witnesses for solving the other problem. Okay, so now we solved the first problem. We found enough relevant sets such that H is epsilon over 3 close to F. Now we want to solve the second problem. That is for any assignment X to find the value of the relevant coordinate in Xij of X for all J. So now we have H and at most k relevant sets of coordinates. Assume without loss of generality that the relevant sets are x1, x2 up to xk. We define G that is equal to H, where we project all the variables in xj, in xi, to the relevant variables in this set. We also have for every relevant variable a witness Vj. Now the algorithm goes like this. We define eta jx equal h, where we project xj to the vector x and the other variables to the witness vj. We test if eta jx is 1/8 close to a literal with respect to uniform distribution for every j. If not, then we reject. Now we claim that for a random uniform z with probability at least 3/4, x tau j is equal to eta j x plus z, here plus is bitwise XOR eta j z. This is actually the self-corrector. Okay, let's see what happened when h is in C. When h is in C, eta in Vj is equal to h in Vj. And eta in 0 is this. And notice that those two are not equal. So since V is a witness, they are not equal. Now since xj contains only the relevant variable x tau j, eta j depends only in this variable. So eta j is either x tau j or x tau j naught. In this case, it is easy to see that the self-corrector gives x tau j with probability 1. For any random z with probability 1, we have x tau j. Now for any other function h, the tester either reject when it tests that eta j is 1/8 close to a literal with respect to uniform distribution, or if it is 1/8 close to a literal, then it is easy to see that the self-corrector for a random uniform z returns the value of the variable with probability at least 3/4. In both cases, the value of x tau I can be found without learning tau I. Now, of course, we can boost this probability in a standard way. So we now also solve the other problem. This is the first tester in the paper. We also study testers of classes that can be approximated by k-junta under the uniform distribution. For many of those classes, we find a tester with optimal query complexity. For example, the class of DNF with S terms, which is not a subset of k-junta, but can be approximated. We run the first stage in the previous tester, but this time we do not take a zero projection, we take a random W projection. The reason is that the large terms, that is the terms that contains more than order log S variables in the DNF are zero for a random projection. So we run the first stage, this same procedure. We find enough relevant sets such that this time H f hat is epsilon over 4 close to F. F hat is a DNF with at most S terms and contains only the influential terms, that is terms that of size at most order log S. So now we have a function that depends on order S log S variables, which is a subset of order S log S junta. Order S log S is independent of N. If F is epsilon far from the class, then hat F is 3/4 epsilon far from the class. If F is in the class, then F hat is also in the class, because a random projection with W of DNF gives a DNF. And then after that, F hat is in the class order S log S junta. So we use the previous tester to test F hat. And thank you very much.